Okay, welcome back, CIS 123. This is our second week, and we have packed agenda. Any questions before we begin? Okay, so let's get started with the material. This is obviously our one of the websites I have for you, and it has a link to CIS 123. Our bulletin board is posted. This is our week 2. There are some leftovers from the presentation that we were running last week. I think I would like to quickly revisit the numbering systems that we mentioned at the end of the week. And for this, I am going to basically go to a drawing board and remind you that we talked about the binary systems. We talked about the octal numbers a little bit, and we also talked about hexadecimal numbers. So the hexadecimal numbers are simply a row of digits from 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And apparently I'm going to run out of space here, so I'm just going to basically maybe switch to a smaller pen to have more space. All right, so hexadecimal 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we run out of digits. So in hexadecimal world, to compensate for the lack of the remaining digits, that altogether we need 16 digits in that world, we say A. You can also use lowercase a, and then B, C, D, E, and F. Okay? So in decimal world, this is simply 0 through 9, okay? And A is 10, and B is 11, 12, 13, 14, and 15. So altogether, from 0 through 15 in decimal world that we know, in hexadecimal world, all of these numbers, all of these digits, and then numbers from 10 to 15 are represented by a single hexadecimal digit, which includes 0 through 9 and then A through F. So basically, if I ask you what was C in terms of the decimal number, the answer is it's 12, right? It's just decimal 12. Now, you may be wondering why we're discussing it this early, and the reason is because we want to essentially use hexadecimal numbers to encode difficult to deal with patterns of binary numbers. In fact, I can try to write down a row of binary numbers that represent all these digits in form of 0. Obviously should be 0, 0, 0, 0, all zeros, right? 1 is 0, 0, 0, 1, okay? 2 is 0, 0, and then 1, 0, because that's naturally what comes next after 1, 0, 0. Okay, so then I can write 0, 0, 1, 1, then I can write 0, 0, I'm sorry, 0, 1, 0, 0, okay? Because after 0, 1, 1, all ones are filled. I have to use the higher position, which is 1 in the second placeholder here, and then 0, 0, and then obviously 5 would be 0, 1, 0, 1, right? And then 0, 0, 1, 1, 0, 7 would be 0, 1, 1, 1, okay? And then finally 8 is 1, 0, 0, 0, and then you see that it's just basically exhausting all possible combinations of zeros and ones, but following some disciplined approach to this, and it comes from the fact that basically here the right-hand side is the lowest digit, and on the left-hand side, this is the highest digit that we use in binary, just like in decimal world. And we can keep going with this, and it's basically going to be 1, 0, 0, 1, then 1, 0, 1, 0, then 1, 0, 1, 1, and then 1100, and then 1101, I guess, and then 1110, and finally 1111. Everything is filled, okay? Everything is filled. So if you then ask me, what is hexadecimal number AB35, okay, this is how I'm going to approach this. The answer is going to be extremely simple. I have no idea what, you know, I'm not in business of memorizing any of this, but having this table available to me, I can tell you that A pretty much is 1010, okay, so 1010, this is what A contributes. Okay, what B contributes is right here. It's 1011. Okay, from my own table. I built everything from scratch. I never looked anything up. Right, so B is 1011. Right here, 1011. Okay, then 3 is 0011. 0011, and 5 is right here, 0101. Okay, 0101. This is it, right? Arguably, it's difficult to deal with binary numbers, but it's much easier to basically look at the, if you want, a compressed format of binary patterns in the form of hexadecimal combinations of hexadecimal digits. Of course, you can do computations in binary format. You can do computations in hexadecimal format. In our case, we're going to limit our use of hexadecimal numbers just because your C compiler, your C++ compiler, your Java compiler, and almost any other system, when it wants to display you an actual address in memory, it's going to use by default hexadecimal format, because internally computers use binary numbers to describe addresses in memory, and hexadecimal format is just compressed version of this long, messy looking pattern of zeros and ones. Okay, so this is just essentially, and I can tell you this, that another advantage here is that if I have another address like AB37, for instance, right? You can see that those are probably relatively close addresses in memory, because AB35, AB37 in hexadecimal world probably not too far apart from one another. But I can, by looking at these two hexadecimal numbers, I can essentially measure and count how many memory locations apart are these two memory addresses. So sometimes it's another task that you have to do with addresses is just simply compare them and see how drastically far apart or how close to one another they are, or sometimes if this is the same address, right? So if I had two versions of AB37, I can say, oh, that's the same memory address. Apparently, somehow I have indicators that point me to the same memory address. All right, so that's pretty much it. This is all I wanted to let you know, is that we are going to continue using hexadecimal numbers. There's really nothing to be scared of when you look at hexadecimal number. And if you build this table, and of course we have it part of our presentation, for instance, on our website, if you go, simply click on the schedule and you go to week 1, and at the end of presentation, I'm just going to open the handout format here, right? So at the very end of this presentation, I have this table nicely printed for you. Well, I wish our network connection was a little faster than that. But at the very end of this, you can see that there is, just trying to making it a little larger, as you can see that on top of everything, I also snapped on the octal numbers, but these are the hexadecimal numbers from 0 to F. That looks much easier than the one that I was drawing by hand, right? The decimal numbers, and anytime you see some unfriendly hexadecimal number, just remember we use it only because this is arguably 8 is a better alternative than 100, okay? Because it's much harder to memorize 4 digits, even though they're binary digits, than just one digit, or when you need to compare those numbers, right? So anytime, just remember that anytime you do a conversion from hexadecimal to a binary version, all you do is just remember that each hexadecimal digit, such as A, B, 3, and 5, contributes four binary digits to the ultimate answer, what this bit pattern is in terms of zeros and ones. Another excellent help that you can get from your system is to go to a standard desktop calculator, if I can spot where that is, right here, right? So this is the calculator, and in calculator, let me just minimize this to not to obscure anything that we'll look at. So this is the calculator. I usually normally switch it to byte size. You can see that it currently displays 8 digits. So 0 is basically in byte size, which is 8 bits, is 0, 0, 0, 0, 0, 0, 0, 0, 8 zeros. Okay, if I here I can switch between the hexadecimal notation, the decimal notation, even octal if I need to, and of course the binary notation. And so if you see how in binary, of course, all keys are disabled except 1, 0, 1, 0, whatever that is, right? If I'm typing this in, clearly, you know, you can just switch to the hexadecimal format and see what that number is, right? So that number was 2A, okay, and that's you can still see the binary pattern still displayed as 0010, 1010, and sure enough, A contributes 1010 and 2 contributes 0010, and you get this type of encoding, right? So if I switch to a decimal, click the clear button and just you know, punch in some numbers like that to oh, actually it doesn't let me type because I'm currently in byte format. If I need bigger numbers, I need to switch to 16-bit maybe data type, and then type some of my, you know, numbers to make it look like that, right? And then I can again switch to hexadecimal, and this is what it is. And clearly, it's easy to use the calculator to do conversions and be comfortable with it. In fact, in your quiz, I'm asking you to use your calculator to do a few conversions. So don't be shy to open your desktop calculator, switch to, I think you need to switch to the programmer mode if you do this on Windows, and there are similar options on your Linux platform and on your Mac platform. Pretty much the same arrangement, just make sure that, that all of these numbers are visible and use it. Now, I actually, at some point, I discovered something interesting, is that you can actually click on these digits right here and modify their values. See how I can flip 0 and 1? If I just simply click on the bit pattern that is displayed for me there. This is a cool trick that you can use to like do some tweaks when you work with binaries and some other format right away. So anyway, this is something to be aware of, very useful, and I think I went to talk again, like second take on our conversation about hexadecimals versus binary versus decimal, pretty much in order to let you know that there's nothing to be afraid of when you see a hexadecimal number. You really, it's in a way, it's just a bit pattern that you just have a chance to see, and if you really want to interpret what that number is, just switch to a decimal format. Okay, 7,672. Okay, so that's just, you know, just a number. Whatever it represents, it represents.